Fine-tune a large language model and it gets cocky, confident even when wrong. That is overconfidence, and it breaks trustworthy deployment. The classic fix is Bayesian. Put a distribution over the weights, capture your uncertainty. But a Bayesian pass over billions of parameters is prohibitive, and keeping a deep ensemble of full models is worse. LoRA-based Bayesian methods exist, but they put uncertainty over the LoRA adapter matrices, which adds overhead and still treats the rank as a fixed knob. This paper makes a cleaner move. Put the uncertainty on the rank itself. DALorRA. Data adaptive lower rank adaptation. Standard LoRA writes the update as B times A, a product of two low-rank matrices. DALorRA wedges a stochastic diagonal mask in between. Delta W equals B times D times A. D is a diagonal of zeros and ones. Each entry switches a single rank, one component on or off. Treat those entries as latent variables with a Bernoulli prior, learn a Bernoulli posterior by variational inference, and you have just Bayesianized the rank of LoRA, nothing else. The math unfolds nicely. Delta W is the sum over rank of Z sub j times the outer product of the jth columns. Each rank 1 term is a tiny subnetwork gated by a stochastic weight. During training that is a parameter-efficient Bayesian network, capturing epistemic uncertainty and pruning capacity it does not need. At inference, you sample M masks, average the predictions, and it behaves like a deep ensemble of diverse rank 1 configurations. One trick, two theories, both for the price of a diagonal. The headline, on Llama 3.18b across 10 common-sense reasoning settings. On expected calibration error and negative log likelihood, DALorRA is best or second best on 9 out of 10. And it does not buy that calibration by dumbing down. Accuracy stays competitive, best or second best on 5 of 10, including under distribution shift, train on one benchmark, test on chemistry and physics it has never seen. The counterintuitive lever. You might think any rank dropout would do. It does not. Fix the rank at 8 and randomly zero out. K diagonal entries every step, a rank level dropout. Even tuned to its best K, random masking loses to the learned posterior, and the best K swings wildly by task. Too much masking starves capacity on one benchmark, yet slightly helps another. A fixed dropout cannot find what the data wants. Only the learned posterior can. The efficiency surprise. DALorRA adds 520 trainable parameters. Negligible. Less than the Bayesian adapter methods it beats. And because the mask sparsifies the update, training is actually faster than vanilla. LoRA 0.72, 0.60, 0.65 of LoRA's time across 3 benchmarks. Better calibration, fewer parameters, and quicker. The sparsity is not a cost. It is the mechanism. 2 more findings. First, capacity plus sparsity. Raising the maximum rank generally improves both accuracy and calibration. The win is not sparse alone or dense alone, it is enough room pruned intelligently. Second, the learned posterior is non-uniform. It varies across transformer layers, across query versus value projections, and across datasets. The mask learns where the rank is actually needed. That is, data adaptive rank allocation, not a handset budget. 4 honest caveats. First, this is classification over fixed answer sets, not open-ended generation where uncertainty is messier. Second, inference needs M equals 10 mask samples, real overhead for latency-sensitive use. Third, uncertainty lives only at the rank level, not over individual adapter weights, so it may miss fine-grained weight uncertainty. Fourth, the posterior assumes independent Bernoullis, ignoring dependencies across ranks, layers, and projections. Structured posteriors are left for future work. Honest framing. The reframe is the contribution. Stop Bayesianizing the weights. Put the uncertainty on the rank. DALorRA wedges a stochastic diagonal mask into LoRA, learns a Bernoulli posterior over it by variational inference, and trains an ensemble of rank 1 subnetworks for free. 520 extra parameters, faster than vanilla LoRA, and best or second best calibration on 9 of 10 settings. Calibration was never about more capacity. It was about knowing which rank components to trust.